Hello and welcome to lesson 4 in the alkenes topic. So this lesson is really all about the mechanism of electrophilic addition. So this is basically a detailed kind of behind the scenes look at how addition reactions that we looked at in lesson 3 work. If you haven't watched lesson 3, you're not familiar with addition reactions, then you need to go and look at that first, because it's going to assume some knowledge about how double bonds in alkenes are reactive and the fact that we can use symbol equations to show how addition occurs at a double bond. Okay, but obviously this takes it into a bit more depth. Before we do that though, as usual, some warm-up questions. Here they are. So we've got a recap question on the sort of geometry of ethene, or the carbon atoms in ethene, and then we've got an amount of substance question, a moles question. So the context for the moles question is alkenes, but in reality it's just a moles question. Pause the video and have a go at these, then we'll talk about the answers. Okay, so let's have a look. Ethene is considered to be trigonal planar, or the carbon atoms in ethene are considered to be trigonal planar. Bit of a strange one, because if you remember from the first lesson, the idea is that the double bond in an alkene, or the double bond in ethene in this case, we kind of treat it as if it's a single bond when it comes to determining the shape. Obviously, it's not a single bond. There are two pairs of electrons there. That's very important for this lesson, but you treat it as if it's a single bond when determining the shape. So you act as if it's got this kind of basic X, Y, Y, Y shape, which forms the interior shape of a triangle and is flat. So we call it trigonal planar. For the bond angle, the actual values, it doesn't matter. If you gave 120, that's a perfectly reasonable answer. So then the moles question. You were given the balanced symbol equation. That's significant because it allows you to extract the information that, given that there's no coefficient in front of the ethene or the bromine, that means that they react in a 1-to-1 ratio. That's important because then what you can do is take the value that you were given for the number of moles of ethene, which is 0.04, and say, well, if there's 0.04 moles of ethene, that will react with 0.04 moles of bromine. So that's where this bit of logic comes from. And you might not have started with this bit, but I have, okay? You might have started with the next bit, which is that you're also given the concentration and volume of some bromine water. So it was 1.2 moles per decimeter cubed in concentration and 50 centimeters cubed in volume. And so you can calculate the number of moles of bromine which are present at the beginning of the chemical reaction, which is actually 0.06. So then the next step is to sort of recognize that the bromine is in excess, which makes the ethene the limiting reactant. The reason that's important is the question actually asks you to calculate the new concentration of the bromine water. So after the reaction has occurred, the ethene will have all been used up. Some of the bromine will have been used up, but there will be some bromine left over. And calculating that value is how you're going to calculate your new concentration. The whole point is you start with something that has a concentration of 1.2 moles per dm cubed, and we're expecting a decrease from that value. It's going to go down. It has to go down because some of the bromine is reacting. So there will be a lower concentration of bromine as we go along. So then let's look at how we make that tick. It's a simple subtraction. If 0.06 moles of bromine were present to begin with, that's an excess. We can take away the amount that will actually react, which we worked out in that very first step was 0.04. So just to show you the relationship there, I know it all gets a bit kind of crazy with the blue highlighting, but it's just kind of show you how we're tracking through. That means that 0.02 moles of bromine are now left over, essentially, present at the end of the reaction. That's a significant number because that's now going to get plugged back in to our N equals CV expression, which will be rearranged because the number of moles of bromine is dropped, but the volume has remained constant. Okay, so to calculate the new concentration, we need to take our new number of moles, here it is, and divide it by the same volume, okay, which is 50 over 1,000 because it's 50 centimeters cubed, but we need it in decimeters cubed to make it relevant for concentration. And our new concentration is 0.4 moles per dm cubed. So just a quick reminder about a sense check here. 0.4, that's down from 1.2. Yeah, makes sense, okay, because it's decreased. So it's always worth pointing out, any context is good for a moles question. They crop up everywhere in chemistry. Paper 1, paper 2, paper 3, it doesn't matter where. You can always be asked a moles question. So just because these lessons are teaching you organic chemistry doesn't mean I won't throw in one of these once in a while, right? Because there's always a good opportunity to practice this kind of skill. Anyway, let's move on and go back to the organic. So we're going to look at 3 examples followed by some practice in this lesson. The first example links to something we did last time, which is the reaction of alkenes, in this case ethene, with hydrogen halides, in this case hydrogen bromide. So we've already done this basically, right? We've looked at the structure of ethene and the structure of the product of this reaction, and we've looked at the equations as well. So the reaction type is something we've already considered, which is addition. However, we should also classify the mechanism type, which is electrophilic addition. And this might feel like nitpicking or splitting hairs or whatever, right? And to some degree, you know, fair enough it is, but there's a distinction here. An addition reaction is any reaction where you add something to a compound. Electrophilic addition is a specific mechanism that explains how that occurs, in this case, particularly with alkenes. Just to sort of emphasize what I'm on about, there's also a form of addition called nucleophilic addition, which is not relevant to this topic, but it highlights the importance of not just saying addition. In this case, the reaction type is addition, but the mechanism type is called specifically electrophilic addition. So let's look at how this works, right? We're going to work through one version of the mech with lots of annotation, then the second version with a bit less, and then the third version again with a bit less, and then some practice. Let's have a look at it. So here is ethene and hydrogen bromide, okay? So you'll need to copy these structures, obviously pausing the video as appropriate. I'm not always going to tell you to do that, so you just need to do it when it's relevant. So, right, I'm going to use a little bit of highlighting here. I don't recommend that you do just because it will clutter your diagram, but it might help a little bit with what I'm explaining. You will need to do the annotations that I'm doing though. So the blue section here that I've highlighted is very clearly the carbon-carbon double bond. So the thing that we need to remind ourselves of, we've actually covered this already in the previous lesson, but it's worth doing again. So we use this phrase to describe the carbon-carbon double bond in alkenes. We say it's a region of high electron density. What that's basically getting at is there are 2 pairs of electrons there, and actually the configuration of them is more complicated than we need to look at A level, especially at this stage in year 12. But the idea is that there's lots of electron density there because there's 2 pairs of electrons, as opposed to the normal 1 pair of electrons you'd get in a single covalent bond, okay? What that means is there's basically sort of a cloud of negative charge there, and that's what makes alkenes reactive, okay? This region of high electron density is attractive to a class of compounds that we call electrophiles, okay? So the name electrophile, it's quite logical, right? Electrophilic means something that, you know, is attracted to electron density. And that's kind of what we're getting at here, okay? And there are a few different electrophiles we're going to look at. We already kind of know them because we've looked at the overview of addition reactions. But in this first example, it's going to be hydrogen bromide. So then I'm just going to get rid of that to tidy it up a little bit, okay? Change color. Right then, so something that you could look at in complete isolation from the alkenes topic is the nature or character of a hydrogen halide like hydrogen bromide. HBr has this relationship, okay? This isn't something I was asking you to figure out, but it is something that you learn when you're doing all the bonding and structure and intermolecular forces stuff in year 12 chemistry, right? So the explanation here, quite a standard thing that we need to be able to talk about. This relationship exists because hydrogen is less electronegative, pardon me, than bromine. Okay, therefore HBr is a polar molecule. It has a permanent dipole. It has a partially positive end, the hydrogen end, and a partially negative end, the bromine end. That's significant because if we look at the orientation of how I've got the HBr, I've got the delta plus, the partially positive end of the molecule, sort of facing or closer to that double bond, which we just said was a region of high electron density. So if you think about this, it's fairly logical. Why is it that a partially positive end of a molecule should be facing, or in the orientation towards the double bond? What did we just say the double bond was? We said it was a region of high electron density, and electrons are negative. So it stands to reason that we're going to have this kind of orientation with our molecule, or it's going to be a more probable orientation. And actually, this is a setup for the mechanism. So because this is the first time round, I'm not going to say, pause the video now and suggest 2 curly arrows, because you wouldn't necessarily have a clue how it's going to work. You might have an idea, but it's not really fair at this stage. Okay, so we're just going to talk it through. There are 2 things that happen in this first step. The first thing is we have a curly arrow from the middle of the double bond to the partially positive hydrogen atom. What this basically means is the double bond, or sorry, one of the bonding pairs in the double bond is breaking apart, and it's being used to form a new bond between a carbon atom and a hydrogen atom, the hydrogen atom that's in HBr. Because remember, curly arrows pretty much always indicate formation of a new bond, or sometimes breaking of a bond. It depends which direction things are going. At the same time, the hydrogen cannot be bonded to both the carbon, which it's about to be bonded to, and the bromine. What that means is the HBr bond has to break, and we show that by moving the pair of electrons, the bonding pair between H and Br, onto the bromine. That's going to form a negative bromide ion. Again, if you're not sort of comfortable with this, you go back to the first lesson on nucleophilic substitution, where we talked about some of the principles of curly arrow mechanisms and how they work. Because it's all very well and good just learning them, but the idea is you should be able to kind of guess a little bit at what's going to happen when you're introduced to a new mechanism, sometimes at least. So we've got 2 steps there, and we've got lots of annotation here that we're not going to normally do, but it's just for this first time round. Okay, so here's our next section, right? A little bit more to annotate here. It's worth pointing out that the bond that we just talked about that was formed, I'm going to label it as that one. In reality, it could be any of the 3 carbon-hydrogen bonds on the left, but let's just say it's that one that's pointing downwards. So when I said the curly arrow indicates formation of a bond between carbon and hydrogen, there it is. Okay? Nothing to do there in terms of writing down. I just feel like I need to point it out. Then let's talk a little bit about what this thing's called. Again, I wouldn't do the balloon myself if I was doing the notes here. It's just for me to sort of highlight when I'm explaining. This thing is called a carbocation intermediate. So what this is, if you like, if you freeze time in the middle of this chemical reaction, you can imagine that this is what you'd see. It's going to react further, and we're going to get a halogenoalkane. That's what's going to happen. But you can imagine that this is what you'd see in the middle. That's what we mean by an intermediate. And it's called a carbocation because it is a positively charged sort of hydrocarbon fragment. If you look at it, it's got a CH3, a methyl group, and then CH2 on the other end, and a plus. There's a positive charge there. And there's a positive charge there because that carbon on the right, this one, it no longer has 4 bonds. It only has 3 bonds, right? Billy 3 mates carbon. And in this case, what that does is it results in there being a positive charge, okay? Because essentially, the electron that carbon had tied up in the double bond, one of the electrons it had tied up in the double bond, that electron is now being shared with this hydrogen, okay? So that's where it's wound up, which leaves the carbon with a bit of a positive charge. Not a bit of a positive charge, a positive charge. Okay, but that's fine because there's something else that can bond to this carbon, and it should be sort of telegraphed, or not obvious necessarily, but apparent what's going to happen next. We need one more curly arrow, and this time you could have a go at suggesting where you think it's going to go. So you could pause the video and think, where am I going to put that curly arrow? If you don't want to commit yet, that's okay. So what we have is a new bond forming. We originate our curly arrow, right, at the lone pair on the bromide ion, and it is forming a new bond with that positive carbon. So we're forming a CBr bond using that lone pair of electrons. When that happens, we get our product, which is the halogenoalkane bromoethane. And we had this at the very beginning. And we've in fact looked at, like I said, addition reactions already. So this part should be, reasonably kind of, you should be reasonably comfortable with this idea that you've got the hydrogen and the bromine from hydrogen bromide. They're now attached to separate adjacent carbon atoms, having split open that double bond. But now we know a little bit more about how the electron pair movements drive that reaction. The name of this molecule is bromoethane, no number required, because whichever carbon you put it on, it's 1. And if you don't need the number because it's always the same number, you don't include it. Okay, it'd be superfluous. So just bromoethane. Right then, take a moment to digest that because we're about to look at our next example. So our next example is the reaction of ethene and bromine. Again, I'm using the examples that appear in the specification. It could be that your alkene is different. It could be that your halogen's different. We'll look at that when we do the practice. But for now, ethene and bromine. There's a bit of a twist or wrinkle here, okay, which has to do with the nature of the electrophile. So we're not going to label the ethene because we already did that in the first example. So we've already recapped the whole high electron density region, phrasing. What we are going to do, though, is talk a little bit about the bromine molecule. Now, here's the problem, if we want to call it that. Bromine is a non-polar molecule. Okay, so if you think about that, well, that means surely that it can't act as an electrophile, because if it's non-polar, then, how are we going to get this attraction between the double bond and one end of the molecule? And the answer here is, even though bromine is non-polar, imagine that your bromine molecule comes into proximity, gets near to the carbon-carbon double bond in ethene. It can actually be polarized. By the electron density of the carbon-carbon double bond. Okay? So what we're basically saying is, even though bromine is non-polar because there's no difference in electronegativity, it is polarizable, meaning if you put it near to this big cloud of negative charge, then what you get is an induced dipole in the bromine molecule, a bit like the explanation for how van der Waals forces arise, essentially. And one end of it will end up partially positive and another end will end up partially negative. But this is like an effect of proximity. It's to do with how close it is to that cloud of negative charge in the alkene. The reason that this is important is because now, actually, we can continue with our mechanism. The reaction can occur. So this time, you should be able to look at that, and you should be able to look at the previous example, and you should be able to mark on 2 curly arrows because it's still electrophilic addition. Therefore, the position and kind of nature of the curly arrows is going to be the same. So what we should have is an arrow from the double bond to the top bromine, which is partially positive, simultaneously an arrow from the middle of the bonding pair onto the bottom bromine, which is partially negative. We then move on. We've got a carbocation intermediate. This time it's slightly different because there's already a bromine attached on that left-hand carbon, not a hydrogen like there was before, but the principle's exactly the same. You should copy this structure and mark on the next curly arrow because, like I said, you should be able to do it now. Okay, so we get another CBr bond forming. Here's our product. This time the name's slightly different. This molecule is called 1,2-dibromoethane. So this time numbers are necessary, and numbers are necessary this time because there are 2 bromine atoms. And so we need to specify and show that we understand that these 2 bromine atoms are attached to different carbons. So we need to call it 1,2, and then dibromo indicates the fact there's 2 bromines. Just to explain, something else about this, or to mention something else about this, right? You very clearly could not end up with this structure in an addition reaction to an alkene. If you look at it, it just doesn't make sense based on what we've just been learning, right? It's not possible. You couldn't get 1,1-dibromoethane anyway, right? Because these atoms from the electrophile, they have to attach themselves to the adjacent carbons, the ones that were, joined together by a double bond. So they can't wind up like that. In order to make that kind of halogenoalkane, you'd have to do a free radical substitution. Okay, and you'd have to get lucky because it's quite random. So then, no major complications there apart from the polarization of the bromine at the beginning. Next one follows the same pattern but with some additional information. So this is all about the reaction of alkenes and concentrated sulfuric acid. So this was one that we didn't do any equations for in the previous lesson, right? And the reason for that was I didn't want to have to talk about the product, but we're going to talk about it now. All right. The fact is, though, that alkenes will react with conc H2SO4, concentrated H2SO4, also conc phosphoric. All right, but we'll worry about that later on. So they will react. We'll have a look at how that works in a minute and the equations. The first thing to talk about is, in order to do this version of the mechanism, you need to learn the displayed formula for sulfuric acid. Okay, so here it is. We have a sulfur. I'm going to say that's in the middle. Consider it the central atom. We have oxygens, which are double bonded, which I'm pointing downwards, and I'll always do that when I'm doing the mech. You'll see why afterwards. Then single bonds pointing upwards to oxygen atoms, and then single bonds to hydrogens on those oxygens. If this looks complicated, I guess it is a little bit, and the nature of the bonding in sulfuric acid and the ion that you get from it, that's something you look at a little bit later on when you're doing some stuff about period 3 oxides. The main message here is you need to learn this. So you sketch it once, then you come back to it in a few days, you try and sketch it again from memory. And if you can't remember, then you practice sketching it. And you do the same thing over and over again. You make it part of your revision, just like, conditions for cracking or, conditions for the, breaking of a CCl bond in a CFC, that kind of stuff, the knowledge stuff. Put it into that kind of bank of questions because you have to know it in order to do this mech. So there it is. All right. Before we get into the mech, let's talk a little bit about what this reaction makes. So the type of compound that you get when you react an alkene with conc sulfuric acid is called an alkyl hydrogen sulfate. So for example, the one that we've got in this equation specifically is called ethyl hydrogen sulfate, because the alkyl group has 2 carbons in it, so it's ethyl hydrogen sulfate. If that looks a little bit scary, don't worry, it makes more sense when you start to sort of draw it out. But that's the thing you get, an alkyl hydrogen sulfate. And this is why we didn't talk about it much last time, because until you do the mech, it is a bit more complex. Why do we care about this? Well, the thing that's kind of, you know, the end point, if you like, or the end game a lot of the time is, you know, what can you do with this? After you've made an alkyl hydrogen sulfate, like ethyl hydrogen sulfate, you can add water, basically, to form ethanol. Now, there are other ways of making ethanol that we'll look at later on, but this is kind of the relevance, if you like, of this reaction. So the equation for that's shown there. We're not going to spend very long talking about that at all. It's really just to explain why we even look at this mechanism. Okay? So what we're saying is that ethyl hydrogen sulfate can be reacted with water and ethanol will be formed and sulfuric acid will be regenerated. Okay? Like I said, manufacture of ethanol really isn't the main idea of what we're doing here, so we'll come back to it later on. Right then, let's have a look at the mech. So, can you remember the displayed formula for sulfuric acid? If you can, have a go at copying the structure of ethene and putting the sulfuric acid underneath it. If you're not sure, wait a minute. I'm going to do it anyway. But it's a good chance just to see, do I remember this thing that I just said you needed to remember? Okay, so this is how I always tend to do it. Don't worry too much about the geometry. It looks a little bit wonky. It's not actually important. The important thing is I've put the hydrogen, which will also be partially positive, and the oxygen on the left-hand side, nearby to the double bond, because that's where our action's going to be. That's where the curly arrows are going to be. It could be the one on the right. It doesn't make any difference. It's just that I always choose to use the one on the left. So even if you weren't confident with redrawing the displayed formula of sulfuric acid, you should be able to suggest where the 2 curly arrows are going to go, because it's the same mechanism. Okay, might not be obvious what's going to happen where the oxygen is, but you should be able to make a good go at it. There we go. Exactly the same logic as previously. Okay. So once you've done that, we're going to move downwards and look at our carbocation intermediate and what happens there. So again, it looks a bit scary and complicated because it's got the sulfuric acid in it. But actually, if you focus on, where that positive carbon is and where the lone pair is, you'll see what's happening, especially if you've been following the thread of this lesson. So there we go. All right. Then finally, let's just have a little look at the product. So here's ethyl hydrogen sulfate, just a reminder that that's what we call this molecule. If it looks a little bit weird where the oxygen is attached to the carbon, that's because I've condensed what was left in the sulfuric, that's that part of the structure. It's not sulfuric acid anymore, but that part of the structure. If that bothers you, then just to sort of help visualize a little bit, might have to elongate some bonds to make this work. Then effectively, what we've got is that, right? It looks a bit clumsy when it's like that, which is why it tends to be sort of tidied up as OSO3H. All right, but if you did do it like that, it would be absolutely fine as long as you've got all the bonds correct. I'm not 100% happy with my double bond in the bottom right there. I'm going to get rid of it all in a minute, but just to sort of model good practice, it's a bit better like that. So, like I said, the relevance of that has a lot to do with kind of the manufacture of ethanol, and we'll come back to that later on. You don't look at the mechanism beyond that in this context. We will look at the hydration of ethene, which is kind of a related idea, but not now, okay? Not right now. It's not something for this lesson. So the mechanism stops there is basically what I'm getting at. So again, take a minute to digest, right? Because we've covered quite a lot. And then we've got some practice to do. So we've got 4 examples. One of them's in red because it's supposed to be sort of more challenging, and it definitely is a little bit more challenging, but they all follow the same kind of idea, right? I've had to be careful with which alkenes are paired with which electrophiles, and you'll realize why when you move to the next lesson. But all of these should be easily achievable if you've sat through this, done the practice, and copied the examples that we've looked at so far. So have a go. See how you get on. Pause the video and attempt the task. Okay. So ethene and chlorine should look like that. Okay, remember that the halogen can get polarized when it gets near to the double bond, which is why one end of the chlorine is partially positive and the other is partially negative. A halogen normally doesn't have that kind of polarity. Okay, we'd call this molecule 1,2-dichloroethane. So this is the analogy here is we did this just with bromine instead in the sort of examples that we worked through. It's the same example. So propene plus iodine. Again, this is a halogen, so it's the same kind of idea. It's polarized by the double bond, and what we get is 1,2-diiodopropane. This might even be the same example I used when we did the equation task in the previous lesson. Can't 100% remember. Okay. Now, with this, there is actually a complication that we don't know about yet to do with how you draw the carbocation. Okay. I'm not going to explain what that is until the next lesson, but suffice to say, you should really have that plus in the middle. Okay. It doesn't make any difference to the overall product, but actually it does kind of matter that your C plus is in the middle here. We'll learn about why next time. If you did it the other way, then don't worry too much because you didn't know yet, but it's worth pointing out when we're looking at this solution. I mean, the way I've kind of led you to it, there's really no reason why you would have put it on the left, because in every other example we've done, we've put it on the right of, the right-hand carbon as a double bond. So hopefully you haven't, but I'm just pointing out there is an issue with that potentially. So number 3, this is our first hydrogen halide, right? Not much to talk about here. I've partially condensed butyrene. I've put the methyl groups just as methyl groups. It's perfectly valid to do that in a mechanism. You don't have to draw the whole thing. In fact, the bigger your molecule, the more untidy it starts to look if you don't start condensing stuff. So that's why I've not shown all the carbon-hydrogen bonds at either end of butyrene. Hopefully the arrows don't need any explanation. Okay. Product here would be called 2-bromobutane. All right. Again, that might even be the same one that I did in the previous lesson. I can't remember, just without the mechanism last time, obviously. So then the challenge question. All right. I've done mine as a skeletal formula. Obviously, you could have cyclohexene as a displayed formula or something similar, but just to keep it kind of, again, a bit more neat and tidy, I've got my double bond, obvious, but the rest of it, I've not shown all the carbons and hydrogens. So just to be clear, if you did do this, that's fine. I'm not going to draw the entire thing, but this end of it, apologies, would look something like that. Okay. You then have the carbocation that's formed. Doesn't really matter where you've put that plus in this case, all right? But it's the same kind of idea. And the product this time, if you had a go at naming, cyclohexyl, which is a bit of a mouthful, hydrogen sulfate. But it's using the same logic of naming that we've used so far. So there's a lot to cover there, right? Hopefully you've found the sort of pace and level of explanation okay. If not, you can always go back and rewatch certain parts. That's it. Thank you. Bye-bye.